The objective today is to explain how a circuit is used to create a cryptographic protocol. So this is a pretty fun lesson. I think you'll get plenty of visuals to better understand how cryptography works and how passwords are unlocking things, and just in general how circuitry on the motherboard is leading to people gaining or being denied access to certain parts of the computer or network. All right, so picture this. The soccer teams of Lima and Cusco have to decide who gets to be the home team for the championship game. The simplest way would be to flip a coin, but the cities are far apart. You have Alicia representing Lima and Benito representing Cusco. They cannot spend the time and money to get together to flip the coin. Can they do it over the telephone? Alicia could flip and Benito could call heads or tails, but this won't work because if Benito calls heads, Alicia can simply say, sorry, it was tails. She could lie, and Benito would be none the wiser. Alicia is not naturally deceitful, but this, after all, is an important contest, and the temptation is awfully strong. In the end, all Benito has to do is guess even or odd. So as a quick refresher, we have and OR gates inside of circuitry. The rules of AND gates and OR gates are simple. Each gate has two inputs and one output. Each of the inputs can be either a 0 or a 1, which can be interpreted as false and true, respectively. So here is what the algorithm essentially looks like. And we'll come back to this picture a little later in the lesson. The way that this circuit can be used to flip a coin by telephone is as follows. Alicia selects a random input to the circuit, consisting of 6 binary digits, 0s or 1s, which she keeps secret. She puts the 6 digits through the circuit and sends Benito the 6 bits of output. Once Benito has the output, he must try to guess whether Alicia's input has an even or an odd number of 1s. In other words, he must guess the parity of Alicia's input. Your think right share here is what number must be kept secret and what number will be sent to Benito. If the circuit is complex enough, then Benito won't be able to work out the answer, and his guess will have to be a random choice. In fact, he could even toss a coin to choose. Now remember, if Benito wins, the playoff is in Cusco. If Alicia wins, the playoff is in Lima. Once Benito has told Alicia his guess, Alicia reveals her secret input so that Benito can confirm that it produces the claimed output. Think right share. To avoid a lie from Alicia, what would have to happen during this phone conversation? So the answer is basically she would need to read off the input immediately, so she herself couldn't figure out what the opposite of Benito's guess is. Looking at this table, here are all the possible inputs with the possible outputs after it. So if she reads off these numbers just really quickly, 0, 1, 1, 0, 1, 1, he can put that into the algorithm and see to make sure that the output that he got, it looks like this. Notice this output right here is the exact same, though the input right here is different. So they could still lie and cheat technically, but the phone conversation is fast and smooth enough, he should be able to pick up on if Alicia is lying to him. There is a simple alternative in which Alicia and Benito construct their circuits independently and make them publicly available. Then Alicia puts her secret input through both circuits and joins the two outputs together by comparing corresponding bits and making the final output a 1 if they are equal and 0 otherwise. In this situation, neither participant can cheat if the other doesn't. For if just one of the circuits is a one-way function, then the combination of them both is always a one-way function. Think right share. What happens when you put two one-way functions together? And to bring this back to the real world, you may have seen settings such as SSL or TLS in your web browser. These systems are based on public key systems that enable your web browser to set up a secure connection to a website such as a bank, even if someone is eavesdropping on all the data being sent. Your think right share here is what two settings can your web browser use to ensure security. And another related concept here is digital signatures. These are based on a similar idea. By making public the output of the circuit for the particular secret input that she has chosen, Alicia is effectively able to prove that she is the one who generated the output, for with a proper one-way function, no one else can come up with an input that works. No one can masquerade as Alicia. See how I often say input and output here regarding cybersecurity? When you're writing your essay on privacy concerns relating to data, you can bring these terms up, these systems up that we've covered in class, because it will be the same whether you're talking about security and privacy on Facebook or security and privacy on a banking website. As a reflection on this particular slide, though, I want you to tell me, what is a digital signature? So you may hear this often if you're watching videos or listening to podcasts about cybersecurity. You'll hear about certification authority. The aim of a certification authority is to guarantee the authenticity of public keys. The way they go about this is the certification authority guarantees the authenticity by signing a certificate containing a user's identity and public key with its secret key. Basically, it's just checking to make sure the math comes out correct. So in order to get this certification authority to agree with what you're doing, all users must have an authentic copy of the certificate authority's public key. To make an actual digital signature, a more complex protocol is needed to ensure that Alicia can sign a particular message, and also to ensure that others can check that Alicia was the signatory, even if she claims not to be. But the principle is the same. So your think, write, share here is, what is a certificate authority? All right, and to wrap up our lesson right before the big project, book recommendation here called Algorithmics. It discusses digital signatures and associated cryptographic protocols. It also shows how to play poker over the phone, which was an idea first raised in 1981 in a chapter in this book called Mental Poker. And another great one is called Cryptography and Data Security by Dorothy Denning, and it's an excellent computer science text on cryptography. The last book is, I don't even know how to say that last name, Turing Omnibus. It has a section on Boolean logic that discusses the building blocks used for the circuits in this activity. And I don't know about you, but I really do enjoy studying the circuits and looking at electrical schematics. It really connects the physical universe for me with the abstract universe of programming. Okay, so project time. You're going to create your own portion of a cryptographic protocol. I say AKA hashing algorithm. It's not a true hashing algorithm, seeing how you can have the same output given different inputs, but we're getting really close. So I'm going to go ahead and leave that in the slide right there. The directions are: using large sheets of paper, you're going to create your own coin flip circuit and briefly explain if you're able to improve upon that and yet make it still just as reliable, if not more reliable than this original one to your left. So you'll get the paper from me, and I will have a bucket full of pencils on my desk, because this is probably one of those activities where you will need an eraser and a pencil. So when you're done with that, bring it up to me. What we're looking to do is end the lesson on this note. What will we see if programmers are inquirers, if they're knowledgeable, if they're thinkers, if they're communicators? You get to choose which one you think this lesson was reflective of and put it in the sentence starter right here. And to officially wrap everything up, think back to the circuit. What actually made this Peruvian coin flip protocol secure?